Hello everyone. In the last class we discussed about moments of random variable. We know that first moment is mean, second moment is mean square value. Today we will discuss about moment generating function. We know that let x be a random variable and we define a function of random variable g of x. So let g of x equal to e raised to sx, where x is the random variable and g of x is the function of the random variable x. That is, it is defined as e raised to sx. Now, moment generating function is denoted as phi x of s, and it is defined as expectation of e raised to sx. Now, we know that e raised to sx can be written as summation over all k sx the whole raised to k by k factorial. Right. So, this equation number 1 can be written as expectation of sigma over all k sx the whole raised to k by k factorial. So, this can be written as s raised to k by k factorial into expectation of summation over all k expectation of x raised to k. Right. So this can be written as, so if you put values of k when k equal to 0 to infinity, right? So if you put k equal to 0, so it will be s raised to 0 by 0 factor, that is 1. 1 plus, when k equal to 1, it will be s by 1 factorial into expectation of x raised to 1, that is expectation of x, plus s square by 2 factorial into expectation of x square plus etc. So this will be phi x of s. So from equation number 2, how will you find the mean value of the random variable x? Now if you differentiate equation number 2, differentiate equation number 2 with respect to s, that is d phi x of s by d of s equal to expectation of x plus 2s by 2 factorial and the expectation of x square plus etc. Right. Now, when s tends to 0 and when s equal to 0, then we can write it as expectation of x equal to d phi x of s by d of s. That is, mean is obtained by differentiating the moment generating function, or first moment is obtained by differentiating the moment generating function for the first time. Okay. Now, similarly, the second moment is obtained by differentiating the moment generating function for 2 times. So, generally, expectation of x raised to m is d raised to m by ds raised to m phi x of s. Okay. Now, if s equal to j omega, then g of x is e raised to j omega x. Now, phi, I am defining a new function, we will call it as characteristic function. Characteristic function, which is denoted as phi x of j omega, which is equal to expectation of e raised to j omega x. Okay, so here also we can find the mean by differentiating the characteristic function. The only thing is, mean is 1 by j d by d omega of phi x of j omega. Similarly, mth moment is obtained as expectation of x raised to m equal to 1 by j raised to m d raised to m by d omega m omega raised to m phi x of j omega. So this we will call it as characteristic function. Put omega equal to 0. Now find the moment generating function for Poisson random variable. Okay, we know that probability that the random variable x equal to k is given by sigma over all k lambda raised to k e raised to minus lambda by k factorial. Now MGF is defined as phi x of s. So this is equal to expectation of e raised to sx. Right. So this will be equal to summation over all k. We know that expectation is e raised to sx into probability that x equal to k. Sigma over all k. Right. So sigma over all k e raised to sk lambda raised to k e raised to minus lambda by k factorial. So this will be k since x equal to k. So the value taken by the random variable will be k. Okay. So this will be equal to e raised to minus lambda lambda e raised to s the whole raised to k by k factorial sigma over all k. So we know that this is e raised to lambda e raised to s, right? So this will be equal to e raised to minus lambda e raised to lambda e raised to s. So this will be equal to e raised to lambda into e raised to s minus 1. So moment generating function for Poisson random variable is phi x of s is e raised to lambda into e raised to s minus 1. So similarly, characteristic function, that is phi x of j omega, can be written as, put s equal to j omega. So e raised to lambda into e raised to j omega minus 1. Now, what is the application of this moment generating function? So we can find mean and variance easily, or we can find the moments easily using moment generating function. Now we will find the mean and variance using moment generating function. So we know that mean is defined as expectation of x is first differential, that is d by ds of phi x of s, and put s equal to 0, right? So this will be equal to d by ds of phi x of s is e raised to lambda e raised to s minus 1, and put s equal to 0, right? If you differentiate this function for the first time, this can be written as e raised to lambda e raised to s minus 1 into, then differential of this, that is lambda e raised to s, and put s equal to 0. So if you put s equal to 0, e raised to s is e raised to 0 is 1. Then here also e raised to 0 is 1. So that is e raised to lambda into e raised to 0 is 1 minus 1 into lambda e raised to 0. E raised to 0 is again 1. So this will be equal to e raised to lambda into 0. So that is 1 into lambda into 1. So this will be equal to lambda. So the mean of Poisson random variable is lambda. So in order to find the variance, we know that variance of x is expectation of x square minus expectation of x the whole square, right? So we need to find expectation of x square. So for finding expectation of x square, we need to differentiate this function twice, right? That is d square by ds square e raised to lambda e raised to s minus 1, and put s equal to 0, right? So this will be equal to d by ds of, so we know that d by ds of this quantity is this thing. So d by ds of e raised to lambda e raised to s minus 1 into lambda e raised to s. So how will you differentiate this? First into differential of second plus differential of first into second, right? So this will be equal to e raised to lambda e raised to s minus 1 into differential of second is lambda e raised to s itself plus differential of first, that is e raised to lambda e raised to s minus 1 into lambda e raised to s into this lambda e raised to s. So this will be equal to, and put s equal to 0. So e raised to lambda e raised to s minus 1 into lambda e raised to s plus e raised to lambda e raised to s minus 1 lambda e raised to s the whole square. Put s equal to 0. Right. Now put s equal to 0. When put s equal to 0, then this will be e raised to 0, 1. 1 minus 1 is 0. So 0 into e raised to lambda. So this is 1. Right. So 1 into lambda. So this will be equal to lambda plus. So this will be lambda square. So expectation of x square is lambda plus lambda square. So variance will be equal to variance of x is expectation of x square minus expectation of x the whole square. That is lambda plus lambda square minus expectation of x the whole square is lambda square. So this will be equal to lambda. So variance of x is also lambda. Now find the moment generating function for Gaussian random variable with mean mu and variance sigma square. We know that the probability density function for Gaussian random variable fx of x can be written as 1 by root of 2 pi sigma square e raised to minus x minus mu the whole square by 2 sigma square, where mu is the mean and sigma square is the variance. We know that MGF is defined as fx of s equal to expectation of e raised to s of x, e raised to sx, right? So this will be equal to integral minus infinity to plus infinity e raised to sx into fx of x. Fx of x is 1 by root of 2 pi sigma square e raised to minus x minus mu the whole square by 2 sigma square dx. So this will be equal to, so I am taking 1 by root of 2 pi sigma square outside, 1 by root of 2 pi sigma square into integral minus infinity plus infinity e raised to sx minus x minus mu the whole square by 2 sigma square dx. So this will be equal to 1 by root of 2 pi sigma square integral minus infinity plus infinity e raised to 2 sigma square sx minus x square plus 2 mu x plus mu square divided by 2 sigma square dx. Okay, so I will rearrange this the terms inside the this integral as so this can be written as 1 by root of 2 pi sigma square e raised to, so integral minus infinity plus infinity e raised to sigma square s square by 2 plus mu s into e raised to minus of x minus mu plus s sigma square divided by 2 sigma square whole square dx. So this term is already expanded like this. So this can be written as e raised to minus x square minus mu square minus s square sigma square minus 2 mu s sigma square plus 2 mu x plus 2 s sigma square s divided by 2 sigma square. So as we know, this x square is already present here. So this x square is there. then mu square is already there, so here it is minus. Okay, so x square mu square, these terms are present here, then 2s sigma square x, this is also present here, right? Then 2 mu x, this is also present here. So the terms left will be e raised to s square sigma square by 2 plus mu s. So this is the term we added here in order to cancel these terms. Anyway, so this can be written as e raised to sigma square s square by 2 plus mu s into integral minus infinity plus infinity 1 by root of 2 pi sigma square e raised to minus of x minus mu plus s sigma square the whole square by 2 sigma square dx. Right. So we can say that this is also Gaussian. This is also Gaussian with mean mu plus s sigma square and variance sigma square. So this will be the total. We know that integral minus infinity plus infinity fx of x dx will be equal to 0. So equal to 1, right? So this will be equal to 1. So the term left will be equal to e raised to sigma square s square by 2 plus mu s. This is the moment generating function for Gaussian random variable. Now we will find the mean and variance of Gaussian distribution using moment generating function. So we know that how will you find mean? Expectation of x will be equal to d by ds of phi x of s and put s equal to 0, right? So this will be equal to d by ds of e raised to sigma square s square by 2 plus mu s and put s equal to 0. So after differentiating this function, we will get it as e raised to sigma square s square by 2 plus mu s into differential of this thing. So this will be equal to sigma square 2s by 2 plus mu and put s equal to 0. When s equal to 0, this term will be 0 and this term will be 1. So what we left is mu. So mean value of x is mu. Similarly, we will find the mean square value. So mean square value will be equal to d square phi x of s by ds square and put s equal to 0, or which will be equal to d by ds of this thing, that is e raised to sigma square s square by 2 plus mu s into sigma square 2s by 2 plus mu and put s equal to 0. So this will be equal to first into differential of second, that is e raised to sigma square s square by 2 plus mu s into differential of second, that is sigma square plus second into, that is sigma square s plus mu into differential of first, that is e raised to sigma square s square plus mu s into this. So this is square and put s equal to 0. So this will be equal to, so put s equal to 0 means, so e raised to 0. So this will be equal to sigma square plus, so this will be mu square. So now variance of x is expectation of x square minus expectation of x the whole square. This will be equal to sigma square plus mu square plus mu the whole square, that is minus mu the whole square. Mu square cancel, so this will be equal to, so variance of Gaussian distribution will be equal to sigma square. Now please do a homework problem. Find the moment generating function for binomial distribution, geometric distribution and exponential distribution, and hence find the mean and variance of these distributions using moment generating function. Thank you.